Welcome to the deep dive. Our mission is always the same. Take a stack of sources, extract the most crucial knowledge, and give you the mental framework to truly understand a topic. Today, we're getting into acid-base chemistry.
And we are going way, way beyond the high school litmus test. I mean, this is literally the backbone of all chemical reactivity.
Right. It governs everything from, say, why your toothpaste and orange juice don't mix.
A terrible feeling.
No.
But it also governs massive geological cycles, like what controls the CO2 in our atmosphere. It's everywhere.
So what we're really talking about isn't one simple definition. It's more of a conceptual hierarchy that chemists use.
Exactly. Think of it like a set of nested dolls. Arrhenius is the tiny one inside, very restrictive. Then you've got Brønsted-Lowry, which is bigger and fits around it.
And the biggest all-encompassing one is Lewis theory on the outside. Our goal today is to unpack that progression and see why you really need all three.
Okay, so let's start with the classic, the one everyone learns first. Arrhenius. This was back in 1883.
And it's super simple, right? An acid makes hydrogen ions in water. A base makes hydroxide ions.
Hydronium, DLH3 plus Dale, to be a bit more precise, but yes. And a base produces hydroxide.
But you immediately hit a wall with that. I mean, it only works in water, and the thing you're studying has to already have an H or an OH to give up.
That's the killer limitation. So many reactions are left out, which is why, in 1923, we get the Brønsted-Lowry definition.
Yeah.
And it shifts the focus
Away from what's being produced.
to the action itself. It's all about the transfer of one thing. A proton, a Neal H plus $. An acid is a proton donor, a base is a proton acceptor, full stop.
That feels like a small change in wording, but it's a total game changer. It lets us classify things as bases that have zero hydroxide in them.
It absolutely does. Here's the perfect example. Take the fluoride ion, O-stol, you get it from a salt like sodium fluoride.
Okay.
It has no Xi-aries, but it's a proton acceptor. It acts as a Brønsted-Lowry base because it literally rips a proton off a water molecule.
So in that reaction, solvent plus water, the fluoride becomes solid HSL, and it leaves behind an solid base.
And just like that, you've made the solution basic. The base didn't bring the hydroxide, it created it by reacting with the solvent.
Wait, so if solids is the base in that reaction, that means water just acted as the acid.
It did. We call that being amphoteric. Water can swing both ways, which is, what makes it such a special solvent.
And this whole donor-acceptor thing immediately gives us the idea of a conjugate pair.
Yes. When an acid, let's call it Salabin-Beige adder, gives up its proton, what's left behind, the solon, is its conjugate base. And their relationship is, well, it's fundamentally inverse.
So if you have a really, really strong acid, something that is just desperate to get rid of its proton,
Then its conjugate base, the ion left behind, must have almost zero desire to take that proton back. It's very stable and happy on its own.
high desire to lose means low desire to regain.
Precisely. And we can actually quantify that. There's a beautiful mathematical relationship. The acid dissociation constant, Ka, multiplied by the base constant for its conjugate, KDE, always equals a constant for water, Kw.
Which is that tiny number, 10 to the minus 14th. So if Ka is huge, Kb has to be tiny.
It's a perfect seesaw. Which brings us to how we actually measure strength. Everyone knows pH, but that's just a snapshot of the protons floating around.
The real yardstick for how strong an acid is intrinsically is that Ka value, or its friend pK.
Right, pK is just the negative log of Ka. It makes the numbers cleaner. And the key takeaway for you is simple.
Yeah.
The smaller the pK, the stronger the acid.
Okay, so now that we're talking about proton transfers, the big question is, how complete is that transfer? This is the whole strong versus weak thing.
Right, it's all about dissociation. A strong acid, like perchloric acid, alid CH-ClO4, dissociates 100%. Every single molecule gives up its proton.
But a weak acid, like vinegar acetic acid, it only gives up a few.
A tiny fraction, maybe a few percent at best. Most of it just stays as intact molecules sitting there in equilibrium.
Let's use a real-world example here because this can be kind of counterintuitive. What about household ammonia? It's a classic weak base.
It's a fantastic example. If you take a really concentrated bottle of ammonia, say 4.7 molar, you'd think it's mostly turned into ammonium hydroxide, right?
Yeah, that seems logical.
The data is shocking. At equilibrium, only 0.19% of the ammonia molecules have actually pulled a proton off water.
Less than 0.25%. That sounds incredibly weak, but I know ammonia is a really strong, pungent cleaner.
It is. And even with that tiny percentage, the starting concentration is so high that it still generates enough hydroxide to give you a pH of almost 12.
So weak means partial dissociation. It doesn't necessarily mean it has a weak effect overall.
That's a great way to put it. It's a crucial distinction.
Now, for a certain class of acids, the oxyacids, there's this great little shortcut from Linus Pauling for predicting strength just by looking at the formula.
Oh, it's a fantastic rule of thumb. For any acid with the formula THNXO, you just count the oxygens M and subtract the hydrogens N.
And if that number is 2 or more, it's strong.
Generally, yes.
Okay.
Look at perchloric acid, THClO4 4 oxygens minus 1 hydrogen is 3. That's a beast. Nitric acid, THNO3 3 minus 1 is 2. Strong.
But nitrous acid, 2 minus 1 is 1, so it's weak.
And it is. It's a surprisingly effective little tool for a quick check.
Okay, before we move on, let's just circle back to that idea of amphoterism acting as both an acid and a base. Water does it, but what else?
A great example is aluminum hydroxide.
Yeah.
EaLOH, think away. You put it in a strong acid, like your stomach, it acts as a base and dissolves. You put it in a strong base, like in your intestines, and it acts as an acid and it also dissolves.
So its behavior is totally dictated by the environment.
Context is everything, which is the perfect segue to our next section, where the solvent, the environment, becomes more important than the molecule itself.
A solvent leveling effect.
This is where things get really, really interesting. See, water is a great mediator, but it's also a bully. Any acid you put in it that's stronger than the hydronium ion, the H2O play, just reacts completely with water to make H3O plus $.
So in water, super strong acids like ClA, acetyl, Bri, they all look equally strong. Water has leveled them down.
It has. It's like having 3 different supercars, but you're only allowed to test them in a 30-mile-per-hour school zone. You can't tell which one is actually fastest.
So if you want to know which one is the real supercar, you have to find a new racetrack.
A new solvent. You have to move to a non-aqueous solvent, something that's a much weaker base than water, like pure acetic acid. Only then can you see the true differences in their strengths.
And this quest for the true ultimate acid strength, this leads us to the wild world of superacids.
Superacids, defined as any acid stronger than 100% sulfuric acid. The term was coined way back in 1927.
But the famous one is magic acid, right? That name is just too good.
It is. It's a mixture of antimony, pentafluoride, and fluorosulfonic acid. And it got its name from a party trick, almost. A researcher showed it could dissolve a candle.
Okay. Why is dissolving a candle magical?
Because a candle is paraffin wax. It's made of alkanes long hydrocarbon chains. They are famously incredibly unreactive. Normal acids, based on Lake H3O plus 3O, can't touch them.
But magic acid can.
It's so powerful it can force a proton onto that inert hydrocarbon, a process called protonation, which is the first step to breaking it down. It does chemistry that's just impossible in water.
So what's the strongest we've ever made?
That would be fluoroentamonic acid, HSBF. We can't even use the pH scale for it. We use something called the Hammett acidity function, HO, and it goes all the way down to -28.
-28, that's so far beyond the normal 0 to 14 scale, it's hard to even imagine.
It represents an incredible amount of available proton energy, just a raw, unchecked proton donor.
Okay, so that's the extreme end of proton donation. Now we make the biggest jump in our hierarchy to Lewis theory. We leave protons behind entirely.
We zoom out to the widest possible view. The Lewis definition covers everything else. Here, it's all about electron pairs. A Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor.
So our old friend the proton, CH+, is just a specific type of Lewis acid because it's looking to accept an electron pair.
It is. But this new definition lets us bring in all sorts of reactions that have nothing to do with hydrogen.
Like what?
Take boron trifluoride. The boron atom is electron deficient. It desperately wants to complete its octet. So it acts as a Lewis acid and accepts a pair of electrons from a Lewis base, like a fluoride ion, to form diaphoric another. No protons anywhere in sight.
And this whole concept is the foundation for a huge field of chemistry, right? Coordination chemistry.
It is. All those transition metal ions like iron 3+ or aluminum 3+, they're all Lewis acids. They accept electron pairs from surrounding molecules, which we call ligands.
And what makes one metal ion a stronger Lewis acid than another?
It's pretty intuitive, actually. It's physics. A higher positive charge, a smaller size, and for transition metals, a higher electronegativity. All those things increase the ion's hunger for electrons.
Now, here's the insight that I found truly stunning. How this connects acid-base behavior to a totally different field. Redox chemistry. Specifically, stabilizing really high oxidation states.
This is where it all clicks together. A Lewis base is an electron pair donor. So the stronger the Lewis base, the better it is at stabilizing a highly positive metal ion.
Okay, makes sense.
Think about manganese. We can get manganese into a +7 oxidation state, Tex-MA7 plus Ori day, in the permanganate ion, 7NO4. That is a massive positive charge to stabilize.
So it must be bonded to a really good Lewis base, and in this case, that's the oxide ion, 7-opio. But wait, why oxide? Why not fluoride, which is the most electronegative element?
You'd think so, wouldn't you? But fluoride is a relatively weak Lewis base. That single negative charge isn't enough. The oxide ion, with its double negative charge, is an immensely powerful Lewis base.
Yeah.
It's far, far better at donating electron density to stabilize that huge positive charge on the manganese.
Wow. So the strength of the base directly enables the existence of an extreme oxidation state.
Exactly. The most extreme oxidation states are almost always found in oxides, not fluorides, because oxide is just the better base. It's a phenomenal connection.
Let's bring this all back down to Earth now. How does this all apply in, say, our own bodies?
Well, the blood in your veins right now is being kept at a pH of about 7.4. It's a buffer system based on carbonate CO2-1, bicarbonate, and carbonate ions.
And if that buffer fails, you're in serious trouble. Acidosis if it gets too acidic, alkalosis if it gets too basic.
Life-threatening trouble. So buffers, which are just conjugate acid-base pairs at work, are fundamental to life.
The pKi of a drug is also critical, right, for how it gets absorbed.
Absolutely.
Yeah.
A drug's pKa tells you if it's going to be charged or neutral at a given pH. Only the neutral form can easily cross the fatty cell membranes in your gut. So a drug's pKa determines where and how well your body can actually use it.
It's a very practical number. And environmentally, let's talk acid rain. What actually defines it?
Well, see, all rain is naturally a little acidic. Atmospheric CO2 dissolves in it to make weak carbonic acid. So normal rain has a pH around 5.7.
But acid rain is much lower.
Much lower, down in the pH 3 or 4 range. And that's caused by much stronger acids, sulfuric and nitric acids, which come from burning fossil fuels.
Okay, one last technical point I want to nail down. We've been throwing pH numbers around, but in really concentrated solutions, the scale kind of breaks, doesn't it?
It does, because pH, formally, is not a measure of concentration. It's a measure of proton activity.
Activity versus concentration. What's the difference?
Think of it like this. Concentration is how many people are in a crowded room. Activity is how many of those people are actually free and willing to talk to you. In a super concentrated acid, like 12 molar HCl, all the ions are so crowded that the proton's ability to act freely is depressed.
And that's what gives us those weird negative pH values we mentioned earlier.
That's it, exactly. If you calculate the pH of 12 mHCl from concentration, you get minus 1.1. But if you measure its activity, it's actually closer to minus 3.4. The scale has to extend to account for that.
And the main tool we use to quantify all of this in the lab is titration.
The careful drop-by-drop reaction. The key there is knowing the difference between the equivalence point, that's the perfect stoichiometric point, on paper.
And the end point, which is what you actually see in the lab.
Right, usually with a color-changing indicator.
Yeah.
But those indicators only work if your acid and base are strong enough to cause a really sharp, sudden jump in pH on the titration curve. If the change is too gradual, the indicator is useless.
What a journey. We went from the simplest idea of ions in water, up through proton transfers to the extreme world of superacids, and then into the all-encompassing electron pair dynamics of Lewis theory.
And we connected it all the way back to your own blood chemistry and why permanganate is so stable. The big takeaway should be that there's no single correct definition. Each theory is a different lens.
A different tool for a different job.
Arrhenius, Brønsted-Lowry, Lewis. You pick the one that's most appropriate for the chemical world you're looking at.
Okay, so let's leave our listeners with a final provocative thought to chew on.
We established that the oxide ion, 20O2, is an unbelievably strong Lewis base, strong enough to stabilize that crazy Tex-Femin plus real charge. It's much, much stronger than the hydroxide ion. So here's the question. How do chemists do acid-base chemistry in a completely alien environment, like molten potassium hydroxide?
Molten KOH.
Yes. In that superheated, water-free environment, the rules we know are completely flipped on their head. The strongest base you can possibly have is the oxide ion, the lid $2. And what do you think is the strongest acid you can have in that system?
I have no idea.
It's water. A single molecule of water is the most powerful acid available. The solvent doesn't just mediate the reaction. It completely redefines who's the acid and who's the base.